This is our video on test review for implicit differentiation, theorems, inverses, and things like that. And I've already done a video on items 1 through 4, so now I'm going to do the rest of the items on the test review. However, I have another opportunity for you to practice a theorem that is not in your review, so I would strongly encourage you to stop the video, read through this problem, and work through it, and then resume the video to see how you do. So I'm going to begin now. Train A runs back and forth on an east-west section of railroad track. So basically, so far, what I've determined is that I have a train that's just kind of going back and forth on an east-west path railway. Train A's velocity is measured in meters per minute, and I can see that in the table right here. That's train A. It's given by a differentiable function. We had the conversation in the last video about a differentiable function. Differentiability implies continuity. So now I know that this function, this velocity function, is also continuous, where time is measured in minutes. Selected values are given in the table. So we have time and we have velocity. The question is here, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t on the open interval from 5 to 8? Give a reason for your conclusion. So we are looking to verify a theorem here. The question that we have, the theorems that we deal with are the intermediate value theorem, the extreme value theorem, the mean value theorem, and Rolle's theorem. All right, so we have to look at the prompt to determine what theorem that this information is appealing to. Now the question is the velocity, so this is the quantity in question, is the velocity negative 100? So I'm going to go back and look at what I have in the table, and in the table I have velocity. So it's the same function, so I'm asking about y values of velocity. So if I'm asking about y values of velocity, in other words, if these two functions are the same, the velocity function here, the velocity function here, unlike in the last video, we were dealing with Rolle's theorem, but in this one we are dealing with the intermediate value theorem because we're asking if a y value is going to occur on a specific function. The only condition of the intermediate value theorem is that the function, in this case velocity, be continuous on a closed interval. And we have that in this prompt. So let's see the write-up. Hopefully you've done your write-up and you're just comparing. This is a student write-up. This is a real live actual AP problem. So let's see how the student wrote it up, and the student got full credit for the question. The student says yes, confirming that the velocity will be negative 100 meters per minute because, and notice they start by claiming the y values. The velocity at 8 is negative 120 and the velocity at 5 is 40. The function, now that's pretty shaky ground. They should have said v of t is differentiable, and then that whole idea of differentiability led them to continuity, so differentiable, thus continuous. The train's velocity must be negative 100 meters per minute at some point between 5 and 8 according to the intermediate value theorem. To get full credit, you do not have to claim the name of the theorem. All right, I'm going to clear these annotations, and I've actually written a second question to go with the same data. I don't know if I'm going to be able to get this in the same screen. So the question is, do the data in the table support the conclusion that the train's acceleration is 8 meters per minute squared at some time on the closed interval from 0 to 5? So maybe stop the video and write down the question, and then go back and look at the table, look at the data to see if you can make your decision. I'm going to go through it now. So I know from this prompt that I've written down here, and part of the reason I wrote this prompt is to give you that comparison. In the first problem, letter A, or whatever letter it was, the problem about the train's velocity was appealing to the IVT theorem because it was from velocity to velocity. In other words, we're looking at the same function. In this problem, the question is asking, does the data in the table support that the train's acceleration? So notice we are not going from velocity to velocity. We're going from velocity to acceleration, and that makes a difference. So in this case, we're given velocity, but the question is about acceleration, and acceleration is the first derivative of velocity. So we're asking, so acceleration is the instant rate of change of velocity. So what this question is really asking is the instant rate of change going to be 8 meters per minute squared at some time on the closed interval 0 to 5. So I'm going to go back up and take a look at the interval from 0 to 5. And since I think this is going to be, I don't think I mentioned that. Since I'm asking about the instant rate of change, then I think we're appealing to the mean value theorem. So my job is to figure out, is the average rate of change going to equal to the instant rate of change? The instant rate of change is 8. That is what they gave me. So I'm going to go back up to the table and I'm look on the closed interval from 0 to 5. So 0 is here, 5 is here. So I'm going to start with the endpoints. I'm going to do change in y, so 40 minus 0 over change in x, 5 minus 0. That's 40 over 5, which is 8. So lo and behold, yes, the average rate does equal to the instant rate on that interval. So let me come back down here and write that up. Do the data in the table support the conclusion? Yes, I'll follow the student pattern. Yes, the data in the table do support. So I'm going to start with v of t is differentiable, thus continuous, on the closed interval from 0 to 5. Now, I know we only have to be differentiable on the open interval, but if we're differentiable on the closed, we're differentiable on the open, and the prompt says that this function is differentiable everywhere. So we're good to go on that. So I've established the two conditions of the mean value theorem. Now I'm going to show the average rate of change. So I'm going to show 40 minus 0 over 5 minus 0 is equal to 8 is the average rate of change of velocity. So I'm going to say, yes, this is so by the mean value theorem, the train's acceleration is 8 meters per minute squared at some time on the interval from 0 to 5. All right, so that gives you a chance to take a look at the difference of how the question is asked and what you're looking for to distinguish between the intermediate value theorem and the mean value theorem. All right, let's get back into the actual review itself. I'm not going to worry about College Board's comments at this time. I'm going to go on to number 5. In number 5, you have a, I'm going to make this bigger actually, fit to width. In number 5, you were given a cubic function, which is continuous and differentiable everywhere. We are to find 1, critical numbers, 2, increasing and decreasing intervals, 3, local max and mins, good gracious, 4, concavity, 5, points of inflection, 6, we are to justify all of our conclusions, wow, 7, we are to sketch a possible graph of the original function. So here we go. So to find critical numbers, we're going to need to find the, oh, where's my work? Maybe I didn't do the work, or maybe it's on the next page. Let's see, there it is. So first, to find critical numbers, I'm going to find the first derivative by the power rule. So that's what I did here. I'm going to factor to set each factor equal to 0, and I have my critical numbers. I have a name on my number line, so I get credit for that. I have both critical numbers on my number line, so credit for that. I have the signs, and to get the signs, I'm going to choose a value in each interval and substitute into the first derivative. Now, when I choose a number like -3, I'm going to substitute into the factored version. That's the easiest way to get your signs. So when I substitute a -3 into this first factor, I'll get a negative. -3 into the second factor, I'll get a negative, and a negative times a negative is a positive. And on the test, these arrows are required, so make sure you show your arrows, because these arrows indicate what's actually happening with f of x. All right, so I'm going to use that number line to draw conclusions and justify them. So I'm stating the increasing intervals, just reading directly off the number line, but the justification is important. You have to tell me because f prime of x is greater than 0. That's your justification right here. Decreasing intervals, justification. Tell me why you know the function is decreasing on that interval. For the next statement, I have a required sentence for our class, and we're going to state a local max occurs at x equals to -2 and is the y value of h of -2. And because you have to, number 1, you have to establish that you have a critical number, so you have to tell me h prime of 2 is 0. And secondly, you have to tell me specifically that the first derivative changes from positive to negative at x equal to -2. Be precise in your writing. Don't be a lazy writer. You're going to do the same thing for the local minimum, except you're going to tell me that the sign of the first derivative changes from negative to positive. Be precise. Be specific. The second thing you were asked to do is to find the concavity intervals and point of inflection. So I'm finding the second derivative by the power rule, which I did right here. I'm going to set the second derivative equal to 0 to get my possible point of inflection. And in this case, I have one possible point of inflection. I create another number line, and the name of the number line must be there for points. My possible point of inflection has been put on the number line. I chose an interval in each region to substitute into the second derivative. I determine the concavity for each interval. Here I am declaring the concavity, and I'm telling you, I'm giving my justification. You must justify these to get full credit. And in this case, second for concave down, second derivative negative, concave up, second derivative positive. And then lastly, here is my sentence for my point of inflection. Point of inflection occurs at -1/3, f of -1. I reported the point, not really sure why, but I did, because the second derivative at -1/3 is equal to 0, and the sign changes. It doesn't matter positive to negative or negative to positive for concavity. All right, that's number 5. Number 6, we are finding the derivative of various functions. So as promised, we have some inverse trig stuff going on here. So the derivative of arc sine, you should remember, is u prime over the square root of 1 minus u squared. You need to have that memorized. I can see arctan right here. The derivative of arctan is u prime over 1 plus u squared, which you should have memorized. Okay, so for letter A, e to the power of x cubed is my u. So when I do u prime, I get e to the power times the derivative of the power over the square root of 1 minus e to the x cubed squared. Now let's talk about that because the way I wrote it. So e to the x cubed squared. That's one way to write it. But from Algebra 1, when I have a power raised to a power, I multiply the powers. So that's the same thing as e to the 2x cubed. I would take either one of those on a test, but make sure you have one of the correct versions. There's really nothing you can do to clean that up. In letter B, I hope you spy a product. We're multiplying 3x to the 4th by arctangent of 2x. So you could do the first factor, 3x to the 4th, and then arctangent of 2x. The derivative of 3x to the 4th by the power rule is 12x cubed. The derivative of arctangent is u prime, so that would be 2 over 1 plus, and then 2x squared would be 4x squared if you simplify it. And then we're going to crisscross, and since it's a product, we're going to plus. So there is the 3x to the 4th multiplied by 2 times 2 over 1 plus 4x squared, and then the second 12x cubed multiplied by arctangent of x, and of course I can clean up by multiplying 3x to the 4th by 2, and so that's what I did right there. I got 6x to the 4th, and really nothing else can clean up in part B. All right, let's clear these annotations so I can go on to letter C. In letter C, be very careful, I have ln of. So the outside function is ln, so the first thing I'm going to have to do is u prime over u. The inside function is arc cosine, so this is the u of ln, okay? So I'm going to start by finding u prime. So my u prime equals, so let me start my derivative right here. So if it's u prime over u, I can go ahead and put the arc cosine of 2 to the x down here. That's my u. I just have to find the u prime. Now for u prime, the derivative of arc cosine is negative, because it's a u over the square root of 1 minus u squared. But I have an inside function of 2 to the x, so I have to do the u prime in red. So that's going to be the derivative of 2 to the x. It's an exponential, is 2 to the x, ln of the base, times the derivative of the power, and the derivative of the power is 1. So that's my negative. That takes care of the u over square root of 1 minus, this is my u for this part, u squared, so that's 2 to the x squared. Now that can be rewritten a little bit as negative 2 to the x ln of 2 over square root of 1 minus, remember we talked about that power to power, you can multiply the powers, 2 to the 4x. So all of that goes into the numerator here. All right, so let's take, well, let me go ahead and I'm going to bring that over actually instead of taking, so I'm going to bring this denominator over, so that's arc cosine of 2 to the x, and then that's over 1. So I have a fraction divided by a fraction, So I'm going to multiply by the reciprocal, so that's 1 over, and that's going to be that arc cosine of 2 to the x. And so that's how in my answer the arc cosine ends up in the denominator with the square root of 1 minus 2 to the 2x. Did I not? Oh, that's not a 4x back here. I just found a mistake. So 2x times 2 times x is 2x. Glad I saw that. Okay, let's clear the annotations, and now we're going to a symbolic derivative. So we have r of x, and we have a table of values down here that we're going to use, and that table of values has f in it. Oh no, that goes with number 7. Never mind. This is just a symbolic derivative. Thus the lines. So for r of x, we have ln, and the derivative of ln is u prime over u again. So I'm going to do it right down here. This is my u. So when I do u prime, this is a chain rule, so I have the derivative of the outside, g prime of 2x, times the derivative of the inside, which is 2. So that's my u prime over u, which is g of 2x. So that's u prime over u, plus, now I'm going to do the derivative of arc cotangent, which is going to be negative u prime over square root of 1 minus u. Notice you need 2 parentheses there because it's the whole quantity of g of x squared. And the only thing that I could do is I could stick this 2 right here in front. I'm not going to get a common denominator or anything like that. Let's make sure I agree with myself down here. I did write the g, instead of doing the parentheses, I put the square on the g, which is also okay. So that's problem number 6. Okay, here we go. We promised inverses, so I want to make a smart chart, and partner points on inverse functions have reciprocal slopes. So we need to make sure that we know those 2 reminders. So R and F are inverses of each other. Not sure, I don't think the R is actually coming into play. Yeah, I don't think so. I think we just have F and F inverse. This R doesn't come up in the problem. And this is asking me for the derivative of the inverse at 4. So 4 is an x value of the inverse. So that goes there. And from Algebra 2, if you are an x value on one of the partners of the inverse, you are a y value on the other. So that means I have a y value of 4 on F. So I'm going to come over here to the table, and I'm looking for a y value of 4, which is right here. And the corresponding x value is 3. So I can do a 3 here and a 3 here. That's my Algebra 2 maneuver. Now I'm going to use the table to find the derivative of f original at 3. So the derivative, here's 3, and the derivative of 3 is 2. Partner points on inverse functions have reciprocal slopes. So if the derivative of f original at 3 is 2, the derivative of f inverse at 4 is going to be the reciprocal of that, which is 1/2. Okay, moving on. Yep, I agree with myself. Yes, that's always a good thing, I guess. Number 7. Okay, I don't have that worked out, so I guess I'll work it out right now. Let me see how far this actually goes on your review. Okay, so in number 7, this is where we're going to use that R and F inverse thing, because in number 7 we are going to be dealing with the little r function. So little r and f are inverses of each other, and I'm supposed to be finding the derivative of big P at 4. So right here I see a product. I'm going to rewrite this as little r of x multiplied by negative x squared plus 5 f of x to the 1/2 power. So when I find the product, I'm going to come down here and work right here. I have a product rule. Actually, I'm going to write my factors over here. I have r of x, and the derivative of r of x is r prime of x. And the second factor is negative x squared plus 5 f of x to the 1/2 power. So by the chain rule, that's going to be, derivative is going to be 1/2 of the quantity, negative x squared plus 5 f of x to the negative 1/2 power multiplied by the derivative of the inside, which is negative 2x plus 5 f prime of x. Okay, now I'm going to transfer my numbers into that. Let's go slowly. So p of 4 is going to be first derivative second. So I need r of 4 times 1/2 of, I'm putting 4 in place of x, so that's going to give me negative 16 plus 5 f of 4 Alright, so f4, and that's going to be to the negative 1/2 power. The key here is to go slow. Alright, so I'm substituting 4 in here, so that's going to give me negative 8 plus 5 f prime of 4. Alright, that's the first term, plus, because we're doing a product, the second. So now I'm going to come over here. So that would be r prime of 4 times, substituting, I can't believe I said substituting a 4 here. That'll be negative 16. Hopefully I'm not going to run out of room. Plus 5 f of 4 to the 1/2 power. Okay, now I'm going to need to go, if you're smart, make a chart and partner points. So let's see what's going on here. So here's my chart. I have f is the original. Let me do this. I have f and r. They're inverses of each other. I'm going to, right here I can see I need r of 4. And back here I need r prime of 4. So 4 is a value of x on r. It's a value of y on f. And so as we did earlier, we're looking in the f column. We see a y value of 4 and an x value of 3. Meaning here that the y value of r is 3. And it's basically the same problem that we did before. The derivative at 3 is 2, so f prime of 3 is 2. Therefore, r prime of 4 is 1/2. All right, so let's go start filling in the values that we know. So p of 4 is, first of all, we need r of 4, which is 2. We're multiplying by 1/2, so I'm going to go ahead and make that 2 times 1/2 is 1, so that's basically gone. All right, so on the inside I have negative 16 plus 5 f of 4. So f of 4, go slow, is 6 times 5 is 30 to the negative 1/2 power. Multiplied by, here I have negative 8. And 5 times f prime of 4, f prime of 4 is 4, so that's going to be 20, because I multiplied by 5. plus r prime of 4, which is right here, so that's a half, times negative 16 f of 4, again, is 6, and 5 times 6 is 30. That's raised to the 1/2 power. All right, cleaning again. Negative 16 and 30 is going to give me, that's 14 to the negative 1/2 power, so I'm going to make that 1 over the square root of 14, got to go slow, multiplied by negative 8 and 20 is 12, plus a half. So negative 16 and 30 is still 14, so that's the square root of 14 in the numerator over 2. So 12 over the square root of 14 plus the square root of 14 over 2. All right, looking at that carefully, I see I made one mistake. So it was right back here. You guys probably caught it right away. R of 4 is actually 3. So when I said it was 2 times a half makes 1, so that's actually 3 over 2. Glad I caught that. So that's actually 3 over 2. And 2 divides into 12 6 times, and 6 times 3 is 18. Now, had I made that mistake on my test, that would actually just been 1 point mistake. But it's important, and you just got to be careful, and you have to go slow, because that just gives you an example of what can happen. So that's number 7. All right, let's go to number 8. Once the annotation's clear. All right, so get your math eyes ready. Use the graph of the first derivative. So g prime is first derivative. It's important to make sure we know what function we're dealing with. And we're identifying intervals of concavity on the original function. That's kind of interesting. Normally we like to use second derivative, but we don't have second derivative. We're having used the first derivative. So I have to think with my math eyes and with my math brain, how do I use the first derivative to get concavity? Well, I remember if the first derivative is increasing, the original function is concave up. If the first derivative is decreasing, the original function is concave down. So I'm not looking for positives and negatives. I'm looking for increasing and decreasing. So on this first interval, I can see that the graph is decreasing. Therefore, in that region, the graph of the original function would be concave down. In this region, the graph is increasing. So on the original function, it would be concave up, decreasing, concave down, increasing, concave up. So g of x is concave up on, let's see, that goes from 2 to, what does that say, 3.25. And from 4, I'll assume the graph goes to infinity because g prime of x is increasing. Notice when I justify with the function that I'm given. Second statement, g of x, g original is, I should have gone blue, but that's okay, is concave down on and negative infinity to 2 and concave down. 3.25, be careful, claim the x values, not the y values. 3.25 to 4 because the first derivative, g prime of x, is decreasing. And finally, number 9, looks like we're going back to another theorem problem. Oh, I had 7b down here. What's beautiful. Oh, I was wondering where those answers were. Number 9, now we have a car on a straight track. We have an interval from 0 to 60. The car's velocity is measured in feet per second. So here we have time. Here we have velocity. And here we have acceleration. They give us the units, and let's see, let me read that carefully. The car's velocity and acceleration are continuous functions. All right. Now, if, I can't really say that. So the table above shows selected values. Letter A. Remember I said earlier, if you see must there be a time, then you better start thinking about theorems. So we got to figure out which one. Must there be a time when the velocity is -5 from 0 to 60? Now be really, really careful with this because this can be a tricky situation. Earlier I said if you go from velocity to velocity, you're talking about IVT because you're talking about a y value on the same function. If you go from velocity to acceleration, then you're talking about MVT. So we have to be careful that if the IVT does not make this work, we have to be careful not to rule out the MVT because we have two sets of data. So for example, when we go, let's block off the interval. All right, so from 0 to 60, we're looking at, let's start with looking at velocity and see if we can make this happen using IVT. Now we already know that velocity is continuous on the closed interval, so we're set for the condition of IVT. Since the y value at 0 is -20 and the y value at 60 is 10, we know that -5 is between -20 and 10. So yes, by the IVT, we can declare that there must be a time when the velocity is -5. So let's take a look at my write-up on that. And here it comes right there. So I said, V of t is continuous on the closed interval. They told me that. I'm declaring the y value on the first endpoint, declaring the y value on the second endpoint, and then I'm writing my inequality where I show my reader that I understand that -5 is in between those y values. Therefore, there must be a time when velocity is -5. You can put your period there, or you can say by the intermediate value theorem if you claim the correct theorem. Just be careful with that. All right, we have one more item to go. So let's get this up here. Let's clear these annotations so that we can start. So in letter B, we're now looking on the same interval. Must there be a time when the acceleration is equal to 0? So my first thought would be, I wonder if I can go from acceleration to acceleration and use the intermediate value theorem. So when I look at, we're trying to get a y value of 0. When I look at the interval 0 to 1 and 60 to 20, I don't really see any interval where, well, first of all, 0 is not between 1 and 2, and I don't see any negative values in these y's that would allow me to enclose 0 in between a positive and a negative. So I'm not going to be able to use the intermediate value theorem to make this happen. So then my only other choice is to think about whether or not I can make the MVT happen. In other words, I have a velocity function. Maybe I can go from velocity to acceleration because acceleration is the instant rate of change of velocity. Maybe I could get the MVT to work. All right, so I'm going to take a look at the velocity, and what I want to try to figure out is, can I make the velocity anywhere on that interval come up with an average rate of change. So I want to know if velocity can come up with an average rate of change of 0. If so, I can apply the mean value theorem. Now, if I look at 60, if I look at just the two endpoints, and I would think if I did the average rate of change there, 10 minus negative 20, that's not going to give me a 0 in the that's not going to give me a 0 in the numerator to give me an average rate of change of 0, because they don't have the same y value. Oh, by the way, if they have the same y value, since I'm going for a 0, I could use Rolle's theorem instead of mean value. In fact, mean value theorem is very appealing to me because notice what I see right here. If I go on the interval from 0 to 25, those two x values generate the same y value, and Rolle's theorem would be met. Now, don't panic. I know it said from 0 to 60, but 0 to 25 is included on the interval from 0 to 60, so we can declare this to be true either by the mean value theorem or Rolle's theorem. I'm pretty sure I chose Rolle's theorem, so let's take a look at the write-up. In number 9, I started by saying v of t is continuous on the closed interval. They gave me that. The next part is a little bit tricky. They told me that a of t is continuous. Since a of t is the derivative of v of t, that means v of t has to have a derivative because a of t is continuous everywhere. So I have to declare that. And I stated how I knew it because a of t is continuous. I declared that v of 0 and v of 25 have the same y value of negative 20. And so I declared this to happen by Rolle's theorem, but I could have used the mean value theorem by showing the average rate of change is 0. So that is the review, and I will also do a video of the extra practice problems to support you. Acceleration, which would be another IVT situation. Let's see if we can make it happen. The y value at 0 is 1. The y value at 60 is 2. Oh no. 0 is not between 1 and 2. But don't give up, because this could be going from velocity to acceleration, and that would lead me to the MVT because acceleration is the instant rate of change. So before I say that this is not going to happen, I'm going to check the average rate of change throughout the interval. See, here's this is a real tricky one. My first reaction would be to take 60 and 2 and 0 and 1 and do the average rate of change. So that would give me change in y, 2 minus 1, which is not going to be 0. So I'd be like, oh no, it's not going to happen. But this says the MVT says it will happen somewhere on the interval. So I can, hopefully you are I spying right here, on the interval from 25 to 35, the average rate will certainly be 0, and the interval from 25 to 35 is included on the interval between 0 to 60. This is really tricky. So because I can make the average rate of change 2 minus 2 over 35 minus 25, equals 0, that declares the average rate of change is 0 on this interval, so we can declare that the instant rate of change will happen or on this theorem either. And then we can do, since it was 0, by the way, we could also use Rolle's theorem or the mean value theorem. Either one will work. Now the question is, are the conditions met? Well, back in the beginning, they told us that v of t is continuous and a of t is continuous. Well, since v prime of t is a of t, since a of t is continuous, that guarantees that v of t has a derivative. Since a of t is continuous, v of t has a derivative everywhere. So that was a tricky one. Let's go to the write-up in 9b. Let's see if I can move this down just a little bit more. There we go. So I start by declaring v of t to be continuous on the closed interval. Then I declare that v of t is differentiable on the open interval, and I tell why. How do I know that? Because they didn't tell me. I have to explain why I know. And I'm going to say because a of t is continuous. I decided to use Rolle's theorem, and so I said the endpoints at, or wait, that's not right. V of 0 equal negative 20. V of 0 is equal to negative 20 is equal to V of 25. Let me see what I declared here. V of 0, or maybe I found another interval where it happened. Oh, I did. Wow, that's interesting.